Spline interpolation. Piecewise continuous function. What do you mean by this piecewise continuous function? So far we have considered different interpolation formula such as Newton's forward and backward formula, Gauss interpolation formula, Stirling and Bessel's formula which interpolates the values of the function fx is equal to y at equispaced nodes, and we have Lagrange's and Newton's divided difference formula which can be used for nodes x0, x1 up to xn which are not necessarily equispaced, and we have also Hermite polynomial with the interpolating points x0, x1 up to xn not necessarily equispaced, which takes care of the value of the function at the nodal points as well as the value of their derivatives at the nodal points. But as the given data set, particularly the yi values, are not free from errors. There must be rounding of errors, there must be observational errors. The higher order differences becomes affected with errors at as already we have discussed. Please note that it was discussed where we have considered noise level in a difference table. This becomes more pronounced when there are large number of data points. This will give rise to higher order differences and several computational complexities will arise. When n is large compared to the order of the true function, then the interpolation polynomial of degree n does not provide the correct result. This polynomial may be highly oscillatory in nature, particularly near the end of the ranges. Please observe this curve 1. We have two curves. One is in red colored continuous curve, which is the curve for fx is equal to 1 by 1 plus x square in the region -2 to +2. The curve with broken lines in black colors is the interpolation polynomial curve for n is equal to 11. You should observe that the interpolating curves has a number of undesirable ups and downs, maxima and minima, although the values are not very different from the y is equal to fx 1 by 1 plus x square, but so far as the slopes are concerned, they differ a lot from the original one. So, although the curve fx is not oscillatory, the corresponding interpolating curve is oscillatory. Not only that, it has also some negative values, but fx is always positive, as is clear from the above figure. All the interpolating polynomial takes care of the values of fx at the nodes, and with Hermite polynomial takes care of the fx and the slope of the function at the nodal point. But what about the curvature of the curve y is equal to fx? Curvature means it associates with the second order derivative of y with respect to x, that is d2y dx2. There is no formula which also interpolates the second order derivative at the interpolating points. To overcome these difficulties, we may try to construct polynomial which match the value of the given function fx along with its first and second order derivatives at the nodes which are maybe equispaced or may not be equispaced. Instead of fitting one single polynomial for all the nodal points, the total interval is subdivided into a finite number of sub-intervals, and one polynomial of lower degree, preferably degree of 1 or degree of 2, not more than 2 is preferable, degree of lower degree be used for points of each sub-intervals. This technique is known as piecewise polynomial interpolation. Let the partition delta of the total range AB be as follows. Delta AB is divided into a number of subintervals by introducing the points x0 is equal to A, then x1, x2 up to xn minus 1 and xn is equal to B. Note that this delta is just a partition and it has nothing to do with the delta operation, that is the forward difference. Don't confuse this delta with that delta. The piecewise polynomial curve can be of order 2, order 1, that is the linear polynomial, order 2 quadratic polynomial, order 3 cubic polynomial, or more than that. It will be wise if we restrict ourselves the degree of the curve to be 1, 2 or 3, not more than 3, because if the curve is cubic curve, then we can take care of the value of the function, the slope of the function, as well as the curvature of the function. Let us see it pictorially in the following graph. Dotted points are the nodal points. The dotted straight lines are the linear curve. The unbroken curve is the quadratic curve, while the dotted curve is the cubic curve. The points x0, x1 up to xn are called the nodal points, nodes, or grid point or breakpoint. The function consisting of polynomial pieces on the subintervals joined together at the nodes is called a spline function. For linear pieces, it is a linear spline function, that is of order 1. For quadratic pieces, the spline function is a quadratic spline of order 2. Similarly, for cubic pieces, we have cubic spline. Let the curve in the subinterval xi minus 1 to xi minus 1 to xi, I is equal to 1 to n, be denoted by six. Then a real valued function sx is said to be a piecewise polynomial of degree k on the partition delta if in each subinterval xi minus 1 xi it coincides with six, where each six is a polynomial of degree k. The function sx is called the piecewise interpolating polynomial for fx on AB if each si interpolates fx in their respective subintervals xi minus 1 to xi. Now observe that at the nodal points xi, x2 up to xn minus 1, that is the internal nodal point, x0 and xn are the end points. x1, x2, xn minus 1 are the internal nodal points. The function sx does not possess any unique tangent. Look at the figure again. We have here some sharp edges at the internal nodal points. So there is no unique tangent at those points, indicating that sx is not a regular curve. We require a regular curve sx. So we have to impose some constraint at the internal nodal points. We shall, however, search for regular spline curve sx in the entire range of AB, for which some additional condition should be imposed at the intermediate nodes and if necessary at the endpoints also. A regular spline function sx of degree m must satisfy all the following conditions. That is, sx is a polynomial of degree at most m in each of the sub-interval xi minus 1, xi, I is equal to 1 to n. The second condition is Sx and its derivative of order 1, 2 up to m minus 1 are continuous in the entire range AB. Hence, we have the following definition. We define a spline is a piecewise polynomial real function Sx over AB to the real field R on the interval AB partitioned by the delta as A to B by the intermediate points x0, x1 up to xn with the endpoints x0 and xn. When S coincides with the Si in the interval, in the sub-interval xi minus 1 xi. Thus, Sx is equal to S1x in the region x0 to x1 is equal to S2x in the region x1 to x2 is equal to Skx in the interval sub-interval xk minus 1 to xk and is equal to Snx in the sub-interval xn minus 1 to xn. The highest order of polynomial Six is said to be the order of the spline S. If xi's are equispaced, the spline is sometimes called to be uniform spline or otherwise it is a non-uniform spline. For a spline of order k, S is required to be continuously differentiable to the order k minus 1 at the intermediate points, interior points xi for I is equal to 1 to n minus 1 and for all j less than equal 0 less than equal to j less than equal to k minus 1 jth order derivatives of pi at xi is equal to jth order derivative of pi plus 1 at the same point xi. Let me give you some examples. Let us verify whether the following functions are spline or not. The first problem, we take fx is equal to x in the region 0 to 1 and is equal to half of x square plus 1 in the region 1 to 3 and is equal to 5x minus 6 minus 8 in the region 3 to 4. So the entire region 0 to 4 has been subdivided into 0 to 1, 1 to 3 and 3 to 4 into 3 sub-intervals. Here S1x is x, that is a polynomial of degree 1. S2x is half of x square plus 1 is a polynomial of degree 2, while S3x is equal to 5x minus 1 is a polynomial of degree 1. We observe that at the interior point, first interior point, that is at x is equal to 1, we have S11 is S21, no doubt, but what about at the interior point x is equal to 3? We see that S2 at the point x is equal to 3 is equal to 5, while for x3 at x is equal to 3 it is 7. So S2 at 3 is not equal to S3 at 3. So Sx, that is fx is not a spline because it does not satisfy the condition that at the interior point 3 the functional value of S2 is not equal to the functional value of S3. It is not a spline. Let us consider another problem. Fx is given to be x square plus 1, a quadratic function in the interval 0 to 1 is equal to 2x square in the interval 1 to 2 and is equal to 5x minus 2, a linear function in the region 2 to 3. Here the interval AB is 0 to 3, n is equal to 4, x0 is 0, x1 is 1, x2 is 2, x3 is 3. We observe that S1 is equal to 1 is equal to S2 at x is equal to 1, S2 at x is equal to 2 is equal to S3 at x is equal to 2. But what about the dashes, that is the derivatives? S1 dash at x is equal to 1 is equal to 2 is not equal to S2 dash at x is equal to 1, which is equal to 4. So the first order derivative does not satisfy the condition, the required condition. So although the values satisfy the condition, internal conditions, but their first order derivative does not. And that is why fx may be termed as a linear spline, but it cannot be a quadratic spline. Let us consider a similar problem like this. Find the value of a and b such that the function fx defined as ax square minus x plus 1 in the region 1 to 2 and is equal to 3x minus b in the region 2 to 3. Here n is equal to 3 and the nodal points are x0 is equal to 1, x1 is equal to 2 and x2 is equal to 3. For a possible quadratic spline, please note that in the region 1 to 2, the function is ax square minus x plus 1 is a quadratic function, and that is why it is a possible quadratic spline. For a quadratic spline, we must have s1 at x is equal to 2 should be equal to s2 at x is equal to 2, which gives an equation 4a plus b is equal to 7. The second condition, that is the derivative condition, s1 dash at x is equal to 2 and s2 dash at x is equal to 2 gives us the value a is equal to 1, so that b is equal to 3. So if we take a is equal to 1 and b is equal to 3, then fx will be a possible quadratic spline satisfying the conditions that the functional value as well as the derivatives value are equal at the intermediate points.